Welcome everyone to this Thursday's Matter talk. I'm Nicole and I'll be your host for today. Thursday's Matter is a weekly virtual meetup welcoming experts from around the globe to explore a wide range of topics that touch on software development and the tech industry as a whole. Today's edition is brought to you by Skills Matter and Tweak. Tweak is a software innovation lab that helps deep tech startups quickly scale their engineering performance and execute on high-risk, high-reward projects with confidence. Tweak's team of engineers are behind today's boldest innovations in machine learning, distributed computing, and biotech. Applying mathematics, computer science, and the methods of open source to software engineering, Tweak stretches what's possible for clients. We're pleased to have one of Tweak's very own here with us today, and we'll jump into the talk really quickly. But before we begin, I'd like to run through a few quick housekeeping items. First, you can find out more about today's talk and our speaker in the link that I've added to the chat feature of this webinar. As this talk is being recorded, that page will also be updated with the video as early as tomorrow. The chat feature of this webinar is also where you can find out more about our partner Tweak and the good work that they do. I'll add the links to their contact info and their site in the chat feature in just a few minutes. Feel free to also use this chat feature, as I see you've already been doing, to leave any comments and learning points, or perhaps just share a little bit about where you're joining us from today. Should you have any questions on the content of the talk for the speaker, however, please place these in the Q&A feature. These are the questions we will be reviewing throughout the talk, and Andrea will aim to answer them at the end. Only questions added there will be considered. Finally, Skills Matter is proud to be part of an inclusive and welcoming community, and we do have a code of conduct in place. I will also add this link to the chat as well. Please bear it in mind when contributing to the chat and Q&A features of this webinar. And now, without further ado, I am pleased to introduce Andrea Condoluci of Tweak, who will be exploring GHC and OCaml compilers with you. Over to you, Andrea.
Thank you, Nicole, and thanks also to Skills Matter, of course, for having me at this Thursday's webinar. And also especially thanks to all the participants, and I hope you find this talk inspiring, and I look forward for all your questions. So let me just share my desktop real quick. All right. So my name is Andrea Condoluci, and I am a researcher in programming languages and a software engineer at Twig.io. Today's webinar is about something that really excites me: compilers for functional programming languages. In particular, we will have a look at two of the most probably famous functional compilers, the OCaml compiler and also the Glasgow Haskell compiler, also known as GHC. You know, more and more people are passionate about functional programming languages nowadays, and for various reasons. For me, for example, as an academic, I love how, in a way, they deeply are rooted in logic, and also how mathematical structures are used all the time to as design patterns, basically. But, you know, we all have been beginners, and we know how it feels like to tackle functional programming for the first time. The learning curve for newcomers is really steep, especially when time arrives to write code that is really efficient. Then knowing the language is not enough anymore. One must also know the compiler, from the type system at the front to the really obscure optimizations in the back. Most of the times, the compilers make all the smart choices for us. Other times, we, as programmers, need to put ourselves in the compiler's shoes to really understand what is going to happen to our program during compilation. This is why I hope this webinar will be interesting for you. It gives an overview of what really happens when compiling a functional program. Of course, there is not enough time to go into all the details of a compiler, but I hope to give you a good starting point. Also, I hope to give you intuitions and also pointers to parts of the compilers themselves that you can explore then on your own. So, well, let's jump straight into it. Today we are going to talk about the OCaml compiler and the GHC compiler. OCaml and Haskell are both high-level, functional, statically typed languages. OCaml and GHC, the compilers, are actual industrial-strength compilers that were born in an academic setting. OCaml, for instance, was created in the 90s at Andrea, which is a French public research institute. And among the creators of OCaml are big names like Xavier Leroy and Didier Remy and other French academics. GHC instead started at the University of Glasgow in Scotland, but now it has a very vibrant community surrounding it. And it's actually possible to propose changes to the compiler itself by open community processes. Among the creators of GHC, you probably heard the British computer scientists Simon Pitton-Jones and Simon Marlowe. Now, of course, both languages and both compilers have big industrial names among their users. But if one could summarize the difference between OCaml and Haskell in one word, well, that would be probably evaluation strategy. Well, they are actually two words, but never mind. Anyway, the different evaluation strategy that these two languages use has actually been the cause of countlessly many holy wars between the two different communities. So for instance, OCaml uses a strict evaluation strategy, which is the strategy used by probably most of the programming languages that exist. Strict means that expressions are evaluated at runtime in the order they occur in the source code, and that arguments of functions are evaluated before a function is invoked. On the other hand, Haskell and GHC is what is called lazy, which is both its strength and also its, in a way, Achilles feet. Lazy means that expressions in a program are not evaluated until they are actually needed. So in case a sub-expression will never be needed, it will never be evaluated, for instance. But anyway, evaluation strategies are not the topic of this webinar, even though, of course, they have an influence on compilation, as we will see later. So how do these two compilers work? Well, any compiler actually does a conceptually simple thing. It basically takes in input a source file written in the programming language of choice, and then it outputs the instructions for the target computer architecture. And you know, what happens in between is, in a way, dark magic, and we actually need to open the glass dome to reveal what is really going on. Well, it's not that magic after all, in a way. So in the rest of the webinar, we will try to divide compilers, divide the steps that each compiler takes in 4 principal steps. So the first part is the first part of a compiler is the front end part, which is composed of two steps. The first one is the parsing, which takes in input the source program and returns what is called an abstract syntax tree. Then there is the typing, which takes in input this abstract syntax tree and returns an internal representation. So in a way, these first 2 steps are the part where the compiler checks correctness of the input program. The first step is syntactic correctness, while the second step is, in a way, semantical correctness with respect to the type system. Then we have the middle end, which includes many optimizations, which are independent of the target architecture. And each of these optimizations takes in input the internal representation and outputs, again, something of in the same type. So again, something in the internal representation type. Finally, we have the backend, which is the real code generation for our target architecture, which simply takes in input the internal representation and outputs the target code for the correct architecture. In the rest of the webinar, we will consider each one of these 4 steps. We will describe it more in details and try to see some examples to have more intuitions. So let's begin from the first one, the parsing. So parsing, as we said, takes in input a source program and then constructs an abstract syntax tree. Now, as you would have probably noticed, I'm using a syntax with double colons, like the one in Haskell, to denote the intuitive type of each transformation step. So for instance, here I'm writing that parsing is of type source to AST. Also, as you see below in the slide, during the webinar, I will provide pointers directly to the compiler's source code, so that if you're curious about, I don't know, the data structures or the algorithms, you can just browse the repositories of the 2 compilers on your own. Of course, it's not for the faint of heart. Also, I will provide some command line options that you can pass to the compilers to have a look on your own at the actual intermediate results of the compilation. So let's go back to parsing. For instance, concerning the OCaml compiler, OCaml takes in input a string and returns something of type parse3. Actually, the output of parsing can be inspected by passing the dparse3 command line option to the OCaml compiler, OCaml-C, as we will see in a second. Something similar happens in GHC. GHC, when parsing, takes in input the string of the source program, and it returns something of type Haskell expression, which has an additional parameter that in this case stands for GHC parsed. So you can inspect the output of this transformation by passing the command line option dump parsed to GHC. Let's have a quick example. So let's consider, for instance, the simplest program that you can write in any language, the Hello World program. You can find it on the left. So this is the Haskell version. We have a simple module called main, where then there is the main function that just prints hello world and exits. So if we try to run GHC on this hello world program with the dump parsed AST option, we get something like what you see on the right part of the slide. Of course, it's not very informative, it's just an AST, but you can recognize some of the interesting keywords. So we see that there is a module definition, which is called main. And then below you see there is a function main, which is defined as the application, HS app, of a variable with a name put string line, and applied to a literal, which is just a string, which is hello world. Something similar happens also in OCaml. So on the left, you can see the hello world program written in OCaml, which is just an expression of print string applied to hello world. And on the right, you can see the output of the compiler with the parse3, dump parse3 option. So as we can see, the parsed tree is just an application of the identifier print string to the constant, which is a string hello world. So of course, I mean, these 2 examples are not very informative, but you start to understand how you can actually have a look at the intermediate results of compilers and see by yourself what in each of the following steps will happen. Now, of course, parsing is not a particularly, I don't know, groundbreaking operation, but there is a way in each programming language to extend the syntax of the language, which of course makes parsing much more complicated. So for instance, in GHC, there are what are called language pragmas, which are a way to extend the syntax of GHC. And there are more than 80 of these language pragmas, which have the shape that you can see on the slide. And they are actually hard-coded on the GHC parser, and they allow you to enable or disable certain parts of the parser, so in the lexer, so in a way to extend the syntax, the base syntax of Haskell. Another way to extend the syntax in Haskell is by means of template Haskell and quasi-quotations. Template Haskell is a framework to do metaprogramming at compile time. So it can be used both as a macro system to generate some code which would be too boring to write with your own hands, but also as a way to embed domain-specific languages directly in the Haskell source code. So these domain-specific languages, also called DSLs, can be parsed by using what are called quasi-quotations. So for instance, here you see two examples. You can enable quasi-quotes with the language pragma that you see on the first snippet. And then we have two examples, one using regular expressions quasi-quotations, and the other one using SQL quasi-quotations. So basically, you can enter any string, any piece of code inside of this delimiting quasi-quotation parentheses, and then they will be parsed actually at compile time. So basically, when you import a quasi-quoter, for instance, the regular expression quasi-quoter, it's written in Haskell itself. So there will be some Haskell code running at compile time to evaluate these quasi-quotations to actual Haskell code. What is actually interesting is that the Haskell code, which can run at compile time, and which is actually interpreted by a bytecode interpreter, can actually perform any operation. So it can also perform I/O, launch missiles. It can basically do everything. So probably template Haskell should be used with a little bit of care. Now, something similar happens in OCaml. Well, for a long time, the only way to extend the OCaml syntax was by using CAML P4, which is an OCaml preprocessor and pretty printer. So CAML P4 could be enabled by the dash syntax command line option. And what it did is it overrode completely the OCaml parser. So the default OCaml parser stopped working, was disabled, and instead the CAML P4 preprocessor would run on the input string and return a parse3 object, which would then be taken, which will then be processed by the OCaml compiler. Actually, since probably last year, CAML P4 has been deprecated, and the alternative is using so-called PPX rewriters. So PPX is an alternative to CAML P4, which differs in the way that it does not actually override the OCaml parser, but it runs after the OCaml parser has parsed the AST. So whenever, first the OCaml parser parses the string to a parse3, and extension nodes of PPX, like the one you see on the slide, which is similar to the quasi-quotations in GHC. These extension nodes are basically not interpreted by the OCaml parser. They must then be rewritten by the PPX system before then the compiler can process the input files further. The way to invoke PPX rewriters is by using the dash PPX command line option and to specify the external program which will rewrite the parse3. All right, so let's go to the second point, which is the typing part. So let's recall that typing is the step which takes in input the abstract syntax tree and returns actually the internal representation that will be used by the optimization steps. So what do we mean by typing? Well, by typing, actually, typing includes different steps and different conceptual operations. For instance, one of these operations is type inference. So type inference means inferring the type of an expression without from the expression itself. So without supplying any type. Typing can also be type checking. So for instance, a user provides a type to an expression, and then the compiler must check whether the type that the user supplied is actually correct with respect to that expression. So together, type inference and type checking are more precisely called type elaboration. And this type elaboration is what compilers usually do by combining these two operations. So let's go straight into it. In GHC, typing includes two different steps. The first one is the renaming, which takes in input a parsed expression and returns a renamed expression. You can explore the output of the renaming part by supplying the dump rename command line option. And renaming actually consists in simply assigning a unique identifier to each variable which occurs in the source code. The second step is the type checking, which takes in input a renamed expression and outputs a type checked expression. In OCaml, these two different steps are actually merged into one single step, which takes in input the parse tree obtained by parsing and returns a type tree, which is the tree containing the type information. You know, Haskell and OCaml have very different type systems. However, if one takes in a way, the intersection of the two type systems, what remains is a fundamental type system called parametric polymorphism. Now, the archetypical type inference algorithm for this system is known as Hindley-Milner. It was actually discovered many years ago in the 1970s. It is quite efficient in practice and very flexible. And in fact, it has been extended to handle more and more complex type systems, like, for instance, Haskell's type classes and more. So now I want to show you a very simple example of Hindley-Milner, of the Hindley-Milner algorithm, just to have just to gather an intuition of how it actually works. So let's say we have a very simple program. We have a function f, which takes in input a variable x, and then returns the variable x plus 42. So of course, any compiler would infer that this function has type integer to integer. Let's just rewrite the function just to make it more clear. So f is fun x arrow x plus 42, which will be more useful later in this algorithm. So what happens with Hindley-Milner type inference? We want to understand how the compiler could conclude that the type is integer arrow integer. So the first step of this type inference is actually assigning a new type meta variable to each sub-expression of the original program. So we have our function f. We just assigned it a new type variable r. We have the first occurrence of the variable x. We assign it a new type variable u, and so on. We have the body of the function x plus 42. We assign it a new type meta variable, and so on and so forth. Of course, there are some subterms of which we already know the type, for instance, addition, or the number 42, which we know is an integer. And we can gather all these typing judgments in order to go to the second phase. In the second phase, instead, we generate constraints, which are basically unification constraints, in which we equate different types that may contain meta-variables. So, for instance, we assigned to two occurrences of the same variable x two different type meta-variables, but of course, the type of x should be just one type. So we can conclude that u must be equal to v. And so on and so forth. So for instance, we assigned to f the type r, which must be an arrow because f is a function, as a function type, which takes in input a variable x, to which we assign the type u, and the body as type s because we assigned it in the first phase. So we conclude that r equals u arrow s, and so on. We continue with all the sub-expressions. We may let guide ourselves. We may let the syntax guide ourselves and go recursively on the syntax of the input program and gather all these constraints that then can be solved by unification. So we apply unification and we solve these unification constraints, obtaining the correct type for the function f. Of course, this algorithm looks quite trivial. And of course, in this case, we have a function f which is not polymorphic. So it's a monomorphic function. And in this case, the algorithm has linear time complexity, actually. In the more general case of parametric polymorphism, this algorithm has actually a pretty high complexity, computational complexity. It has actually an exponential, deterministic exponential time complexity, even though in practical cases, it's quite efficient. Of course, more and more complex type systems require more and more complex adaptations of this basic algorithm. And some extensions of for instance, of the Haskell languages can even make type inference undecidable. So of course, it's a difficult problem. So after typing, we need to get the typed representation of the program to the internal representation. In Haskell, this means going from the type-checked syntax to the so-called core syntax. This happens through an operation called desugaring. In computer science, syntactic sugar means more high-level syntactic constructs that can actually be eliminated, reduced to simpler constructs. And this is the case also for both Haskell and OCaml. For instance, the Haskell syntax type-checked contains a lot of different syntax constructs, but then it's desugared to the core syntax, which actually contains, as a data type, it includes, I think, less than 10 constructors. So it's a very compact syntax. Something similar happens in Haskell. So we have a first step where the type tree becomes a lambda, something of type lambda. And this step includes the elimination of modules and classes and the compilation of pattern matching. So before going ahead, let's have a quick look at these intermediate steps as they are output from the compiler, by the compiler. So let's have a very simple program which just defines a new algebraic data type with two constructors, skills and matter. And then we have a simple function test which takes in input something of the type t and pattern matches on the constructors and then returns a string. So if we invoke GHC on this source program with the dump desugared command line option, this is the output that we get. So basically, we can recognize that we are defining something called test, which is equal to lambda some variable, which has a non very human readable name, and then there is a pattern matching, a case of on the constructors, and then it returns some lower level representation of the strings. Something similar happens in OCaml, and we can inspect it by using the dump lambda command line option. We have a similar program called pattern, which has a type with two constructors and the same function as before. Now, actually, the output of this compilation is slightly different than the one for Haskell, because as we see, the pattern matching in OCaml is slightly decided to do some slight optimization, and decided that basically, since the constructors of the data type don't have any argument and they are monomorphic, it decided that they are just actually represented as numbers in memory. So test has become a function which takes an argument b, and that b is in a way a number denoting the constructor. There is not a pattern matching, but there is just one comparison. There is just one if then else, which checks whether the argument is not equal to 0. So 0 probably represents the skills constructor, and 1 represents the matter constructor. So OCaml is doing some clever optimizations of pattern matchings, which actually are possible because of the strict evaluation strategy, while Haskell is a bit more conservative and doesn't do as much transformation as OCaml. OCaml has an additional transformation phase before reaching the internal representation, which is translating lambda to an f lambda. For Haskell, the internal representation will be the core syntax, while for OCaml, it will be the f lambda syntax. So both core and f lambda are actually inspired by the so-called untyped lambda calculus, more precisely from a type system which is called system F. In the last step that OCaml takes to bring the lambda to an f lambda, the most important transformation that occurs is what is called closure conversion. So this closure conversion is a standard translation of higher order languages, which basically converts nested functions which have free variables, so open meaning having free variables, nested functions, into functions that are closed and are more top level. So let's, for instance, consider this simple function in OCaml, which takes in input an argument and then does an if then else on some Boolean and returns one function in each branch. So we know that functional programming languages are higher order, so they can return functions as output. But of course, if we are compiling to lower levels, this is not possible at some point. So with closure conversion, we get in a way from a higher order language back to something that is more similar to a lower level language. So what happens? Of course, we cannot. Let's take, for instance, the first function. It takes the first highlighted function. It takes in input an n, and then it returns n plus x, where n is a variable bound by that same function, while x is a variable that is bound outside of the function. So it's a free variable in that scope. The goal of closure conversion is to introduce a new argument to each function, which is called an environment, in such a way that all free variables that occur in a function are actually passed in this environment so that they are not free anymore, actually. So for instance, the first function is, say, translated to a function f1, which takes in input itself an environment and also the argument n, which the function was taking before. And in the environment env, we can pass the value of the variable x so that it will be available in the body of the function. After this transformation, both functions f1 and f2 don't have any free variable anymore, and so they can actually be brought into the global scope. Let's go to the third step of compilation, optimization. So both in OCaml and in Haskell, optimizations are performed on the intermediate representation, and they actually consist of a series of passes which take the internal representation into another similar internal representation. So in OCaml, it takes an f lambda and it returns an f lambda, while in GHC is also called core to core because it operates on the core syntax. Of course, there are many optimizations. The most fundamental ones are, for instance, removal of unused code, which is of course fundamental when we have a big program which uses many libraries that are not fully used by our program. Inlining, which is very fundamental, and we will see an example in the next slide, and then others like let floating. So let's have an example of inlining. So let's say we have a pair A, B, which is assigned to a variable x, which then occurs somewhere in our program, but also occurs in a pattern matching. So we have a case x of something. Now, of course, we would like to replace the variable x in the second occurrence so that we have a tuple in the pattern matching. And then this, of course, enables another optimization, which is called case of known constructor, which just reduces the pattern matching and replaces the body, just replaces it with its body, its reduced body. So, of course, inlining is, in this case, for instance, inlining, it's very beneficial because it enabled a further optimization. But when should actually inlining be performed? Well, actually, performing inlining is not always correct. Suppose, for instance, that A or B in the tuple had side effects. So in that case, say for instance, I/O effects or input/output, or they are writing to a file. So if we duplicate we duplicate A or B, this means that the file is written twice. So this is really bad. So of course, every compiler should treat very carefully effects and decide if something can be inlined or not. Now, in Haskell, of course, input/output is clearly signaled at the type level through, for example, monads. For instance, you probably know the I/O monad. OCaml instead does not record effects at the type level. So I think it's interesting to see how OCaml handles effects, how OCaml handles effects. So OCaml has a kind of heuristic way of deciding if something as an effect, and it basically classifies each expression in a program to decide whether it doesn't need to be evaluated or it may be duplicated. And it actually classifies each expression in one of the three following categories. Either no effects. No effects means that it doesn't do anything really bad, and it doesn't write to something which is mutable. And in this case, the expression can be eliminated. The second category is having only generative effects, which is like no effects, but can also allocate in memory. So in this case, it can be duplicated. And there is also a third category, which is the dual of the effects, which is in a way requires to not be able to read from mutable storage. And in this way, in this case, an expression which has no co-effects can be, for instance, reordered. Yeah. Of course, there are many optimizations, many heuristics that each compiler uses to decide what to do, but there is no time to see all of them. For instance, in GHC, there is all these optimizations are collected in an algorithm called simplifier, which is then iterated until fixed point or until a number of iterations is reached. The last phase is the code generation phase, which is the more low-level one. In GHC, it comprises of a few additional steps. So there is the core syntax is compiled to the STG, which is then compiled to C++, which then is output to the target architecture code. In OCaml, it's slightly different because the distinction between native code generation or byte code generation happens right away. So f lambda branches right away in two different directions. Whether you want to compile to the bytecode generator, you want to use the bytecode generator or the assembly generator. Now, of course, there are intermediate steps from going to the high level to the low level of actual stock machines, and both OCaml and Haskell rely on what are called abstract machines. So abstract machines are in a way idealized machines which still have registers, stack, heap, and an instruction set, but they do not correspond to physical machines. For instance, the OCaml compiler uses an abstract machine which is based on the zinc model. And if you're curious and a bit academically inclined, you can have a look at the fundamental paper by Xavier Leroy. Haskell instead relies on the so-called very famous tagless G machine, the STG. And again, if you are interested in this, you can have a look at the original paper by Simon Piton Jones. Now, of course, in the compilation to bytecode, there are many transformations which brings still this kind of higher order lambda language to the real instructions operating on registers, stack, and so on and so forth. So let's consider, for instance, the OCaml native backend generator. So there is first an f lambda to c lambda phase, which basically handles the runtime layout of closures. Then the C lambda is translated to the C minus minus, or better, to an internal dialect of C minus minus. Then there is an instruction selection phase, which selects appropriate instructions for the target architecture and transforms the code into a tree-based representation. Then the machine representation is converted into the linear representation, which basically assigns physical registers to the virtual registers of the abstract machine. It linearizes the machine code, so it's not a tree representation anymore. And finally, it arrives at a representation which is basically assembly. Finally, the assembly file is written to a file. An object file is generated using an assembler from the sister compiler toolchain, and then this object file can be then linked with other object modules or other C code. Yes, obtaining your final binary. So as a conclusion, yes, compilers are hard, especially functional programming languages functional languages compilers. They are hard both because of increasingly difficult type systems, which add, of course, leverage the user from a lot of complexities and help the programmer in many ways, but then the compilers needs to do the hard work for us. But also because of the inherent nature, higher order nature of functional languages. So before concluding, I would suggest you 2 books which I found really helpful, both to prepare this webinar, but also I think they are very interesting for any programmer which is kind of intermediate or advanced and wants to know a bit more about how to do, how the language works and also how the compiler works in a way. So the first one is for the OCaml language, and the second one is for the Haskell language. And well, I thank you a lot for your attention, and I look forward to answer your questions. Let me go
Great.
out.
Thanks, Andrea. I think that
Nicole.
was really good as a high-level comparison, but also still really comprehensive. So naturally, there's a lot more to delve into, but you've definitely given a great view of it. Thank you for that talk.
Thank you.
Like you said, we'll move into a couple of questions now. There is one currently already in the Q&A window. If you want to check it out, we can.
Oh, yes, let me find it.
Sure, no worries.
All right. Okay, there is a question from Manas, which asks, are there any famous attempts at JIT compiling OCaml or Haskell? Well, yes. Yes, actually, I don't know about Haskell personally, but I know that there is research about just-in-time compilation in OCaml, for instance. Yeah, do you have any more specific questions?
Feel free to add your questions into the Q&A window, or we'll give it a couple minutes for now.
All right.
And Andrea, in the meantime, if you have any last comments or tips to delve deeper, feel free to share.
Well, yes, actually, yeah, I was mentioning the 2 books that really helped me a lot, but there are many resources on the internet that everyone can find. Of course, they are a bit fragmented, and it's a bit difficult to find what you're looking for. But a good starting point to know more about these compilers, it can be, for instance, the documentation. For instance, I think the OCaml documentation is really helpful. But also for Haskell, the GHC commentary, which you can find on the Haskell repository, is really contains a lot of resources. Sometimes are difficult to grasp, but I think they are very useful.
Great, awesome stuff. Well, I see you've also put up your email address. So if anybody wants to digest the talk and maybe see the recording after, and then if a question pops to mind after that, feel free to reach out to Andrea directly as well with contact info. Yeah. And also his details will be able to be found on our site tomorrow when we put up the video as well. Here's one more question in the Q&A window.
Yes, a question by Aaron, which asks, regarding Haskell, what phase of the compiler output would you suggest is the most valuable for understanding the performance of a program? Well, this is a good question. Well, I think, of course, I think the optimization phase, because in the optimization phase, the compiler is doing a lot of work to help us in a way, so that many of the high-level things we write then in the end gets translated in efficient code, machine code, but this not always happen. So probably if you if you want to understand the performance of a program, I would try to understand what optimizations are in place, but also, first of all, probably I would try to reason what parts of the program are actually executed at which time, which sometimes can be difficult because of the lazy evaluation strategy of Haskell. So I would probably first reason about my program and only later blame the compiler, probably. So there, I see another question by Robin. How close to optimal are GHC and OCaml when it comes to code optimization, in your opinion? Well, I would not say optimal because, I mean, it's a difficult problem, the problem of compiling, and I think it's a place where a lot of heuristics and you know, dirty tricks are necessary to reach the good performance and the good result. So yeah. Oh, sorry, maybe. Oh, yes, sorry, I got confused by something. All right, sorry. Let's go to the next question. Does the OCaml, by Travis, does the OCaml creating an object file mean that link time optimization can be performed by the system linker? Is there an equivalent for Haskell? No, so yes, for OCaml, yes, you're right about OCaml. For Haskell, it's very different because if you are trying to, for instance, use Haskell together with some C code, then you need GHC to compile both your program, your Haskell program, and the C program. So I think they are different in that respect. But yeah, that's what I would say. I'm not sure about that. The last question by Melvin. Can you elaborate how to parse DSL in Haskell and OCaml? Well, you can probably have a look at the, you know, at the DSL, at the metaprogramming frameworks that I mentioned before in the slides. Maybe you can go back in the video when it's out and see again. But basically, you in Haskell you can use quasi quotations. So you basically you write your DSL as a string inside the quasi quotation parentheses, and then there is an Haskell piece of code which basically parses the string and generates an AST at compile time. Sorry. So basically, how you parse your DSL is your choice. Of course, there are libraries to parse common DSLs like SQL or the regular expressions, as I mentioned, but yeah, Haskell does not impose any way to parse any DSL. Similarly, OCaml, I mentioned PPX rewriters, and it can be any external program which parses your domain-specific language and then outputs an OCaml syntax tree. So it's yeah, there is no right way. You have to find either the right library or write it by yourself. A question by Flavio. Can you explain how monomorphization works? Oh, wow. Well, that's a difficult question. I don't know I can answer right now to this question.
Okay, I think that is something maybe we'll cover offline.
Yes,
for
just
now,
feel free to write me if you have any further
feel free
questions.
to, yeah. Those are his details on the slide that's still being shown now. But for now, thank you all for your questions. That was really good post-talk discussion as well. Thank you, Andrea, once again for joining us today.
Thank you.
You can also find out more about him and on the talk and catch the video tomorrow on the Skills Matter event link that I've shared earlier. For now, we're going to move on to next week. Thursday's Matter will be the same day, same time. I'm going to share my screen so you can have a look at the events coming up. But for next week, we're going to have Matthew Hamilton joining us from IBM, who will be exploring a generative machine learning model that that creates new data instances in the vein of your training data. So have a look at the advanced, feel free to take a screenshot, and we will definitely see you then. For now, it's a wrap for today. Thank you everyone once again for joining, and I'll put up a quick poll on your feedback for your experience today, and we'll see you next time. Thanks.
Thank you.